Hello friends, welcome to UGC EPG Pathshala. I am Divyani Mandloi, Senior Research Fellow at Birla Institute of Scientific Research, Jaipur. Today we shall discuss about Introduction to Digital Photogrammetry, Orthophotos and Orthophotography. The learning objective of these episodes are Introduction to Photogrammetry and Digital Photogrammetry, Techniques of Photogrammetry, Derived Data and Products, Orthophotos and Digital Orthophotography, ortho image generation, and lastly application of photogrammetry. So, starting with the introduction part, photogrammetry as a science is among the earliest techniques of remote sensing. The word photogrammetry is the combination of three distinct words. Photos means light, grammes means to draw, and metron means to measure. The root word originally signifies that measuring graphically by means of light. The fundamental goal of photogrammetry is to rigorously establishing the relationship between the object and the image and derive information about the object from the image. For the layman, photogrammetry is the technological ability of determining the measurement of any object by means of photography. As given by the American Society for Photogrammetry and Remote Sensing, photogrammetry is defined as the art, science and technology of obtaining reliable information about the physical object and the environment through process of recording and measuring and interpreting photographic images and patterns of recording radiant, electromagnetic energy and other phenomena. With the advent of computing and imaging technology, photogrammetry has evolved from analog to analytical to digital soft copy photogrammetry. The main difference between digital photogrammetry and its predecessors, that is analog and analytical, is that it deals with digital images directly rather than photographs. The term digital or soft copy photogrammetry is used when the digital images are used, stored and processed on a computer and giving digital output, that is digital maps, DMs and digital orthophotos. Digital photogrammetry involves processing of imageries of all the types including passive, that is optical sensing, or active, that is radar imaging, and taken from other platform, for example airborne, satellite, close range, etc. The unique advantage of digital photogrammetry in terms of precision and accuracy offers the opportunity for automation of DEM, DTM and integration of images acquired on a multi-platform and multi-sensor basis. Now coming to the techniques of photogrammetry. Techniques of photogrammetry can be classified on two different bases. First is depending on the lens setting. It is further classified as far range photogrammetry, which is with the camera distance setting to indefinite. So next is close range photogrammetry with camera distance setting to finite values. Next is on the basis of type of surveying. This is further classified as terrestrial or ground photogrammetry and aerial photogrammetry. Terrestrial or ground photogrammetry. In terrestrial photogrammetry, maps are prepared from terrestrial or ground photographs. In terrestrial photogrammetry, we take photographs from different points on the earth's surface for measurement purposes. This is mostly close range photogrammetry. The terrestrial photogrammetric survey considered as a further development of plane table surveying. Next is aerial photography. In aerial photogrammetry, maps are produced from aerial photographs taken from air. This is mostly far range photogrammetry. Aerial photogrammetry encompasses two areas of specialization. First is metrical and second is interpretive. The first area is of principal interest to surveyors since it is applied to determine distances, elevations, areas, volumes, cross sections and to compile topographic maps from measurement made on photographs. Second, interpretive photogrammetry, which involves identification of objects from their photographic images and judging their significance. The critical factor considered in identifying objects are shape, size and patterns and shadow. Next is data outputs. First we can derive many information from photogrammetry. So first is determining the scale of a vertical photograph and estimating horizontal ground distance from the measurement made on a vertical photograph. Scale is the ratio of distance between 2 points on a photo to the actual distance between the same point on the ground. Figures illustrate this. For example, if a 1 kilometer stretch of highway covers 4 centimeter on air, the scale would be 1:25,000. Next information we can derive is determination of equivalent area in a ground coordinate system using area measurements made on a vertical photograph. The only difference is that whereas ground distance and photo distance vary linearly, ground area and photo area vary as square of the scale. Next derived data is the determination of object heights from relief displacement measurements. Relief displacement, if the image of the top of the object appearing in the photograph are displaced from the images of their bases, this is known as relief displacement. The magnitude of relief displacement will depend upon, first is flying height. When the flying height increased, the relief displacement will be more. Second is the distance of the object from the nadir point. Nadir point is the point vertically beneath the camera center. When the distance of object is more from nadir point, the relief displacement will be more. Next is the height of the feature. When the distance of object from the nadir point remains same, but the object height increased or decreased, the higher object is more displaced. Next is focal length. When the focal length of camera lens is increased, the relief displacement will be more. Figure 3 explains the height measurement from relief measurements. Next is determination of object heights and terrain elevations by measurements of image parallax. Image parallax, the term parallax refers to the apparent change in relative position of stationary object which is caused by a change in viewing position. The absolute stereoscopic parallax is the algebraic difference, if calculated in the direction of flight, of the distance of two images of the object from their respective principal points. The parallax difference can be used to determine the height of the object and the depth and slope from the stereo pairs. Next information we can derive is to measure the height of an object above or below a reference point from a stereo pair of aerial photograph, following data is required. First is flying height above a reference point. Second is photo base which can be measured from the stereo pairs. Third is parallax difference. It is measured by the use of set of measuring marks, that is also called locating marks. Next information we can derive is the generation of map in stereoplotters. Stereoplotter is an instrument designed for the production of topographic maps from the stereo pairs. Two pictures of a particular area are simultaneously taken but from slightly different angles. The overlapping area of the two resulting photos is called stereo pair. With this, topographic contours can be plotted on map and the height of a vertical feature appearing in the model can be determined. With the advent of technologies, stereoplotter have changed, starting from projection stereoplotter to Kelch stereoplotter to analytical stereoplotter. Analytical stereoplotter is now being used for different analysis. It incorporates a computer which does the work for mathematically aligning the images so that they line up properly. The analytical stereoplotter also allows for storing the data and redrawing at any desirable scale. Examples of analytical stereoplotters are Galileo DigiCard, Intergraph Intermap, Kern DSR series, Wild AC and BC series, Zeiss Plenicom P series, Matra Transfer series, and lastly Leica Photogrammetric suite. Figure 4 and 5 shows some photos of analytical stereoplotters. Next output is generation of digital elevation models and orthophotos. Digital elevation model, as the name indicates, is a digital model or 3D representation of terrain surface. There are three different terms which is frequently being used, that is digital elevation model, digital terrain model and digital surface model. In most cases, the term digital surface model represents the Earth's surface and includes all objects on it. In contrast to DSM, the digital terrain model represents the bare ground surface without any objects. Figure number 6 illustrates this. DEM is often used as a generic term for DSM and DTMs, only representing height information without any further definitions about the surface. Figure 7 explains the surface representation by DSM and DTM. Now coming to the orthophotos and digital orthophotography. An orthophoto is an aerial photograph that has been geometrically corrected or orthorectified such that the scale of the photograph is uniform. Orthophotos are photographs that have been corrected for distortion, which is due to tilting of the camera during the photographic survey, distortion from the camera lens, and relief distortions. Orthophotos display all the valuable information of a photograph, but unlike a photograph, true distance, angles and areas can be measured directly. An orthophoto is an accurate representation of the Earth's surface. Orthophotos have the benefit of high details, timely coverage, combined with the benefits of map, including uniform scale and true geometry. A digital orthophoto is a digital image of an aerial photograph with displacement caused by the camera angle and the terrain are removed. It is thus combines the image characteristic of photograph with the geometric quality of a map. As photogrammetry is the technique of determining the geometric property of object from photographic images, where the 3D coordinates of points, features or objects can be determined by the measurements made in stereo pair using the principle of triangulations. So, the following essential elements required to produce a digital orthophoto are photo identifiable ground control points, camera calibration and orientation parameters. Camera calibration is the process of estimating parameters of the camera using images of a spatial calibration pattern. The parameter includes camera intrinsics, distortion coefficients and camera extrinsics. Next we need is a digital elevation model, a digital image produced by scanning an aerial photograph with a precision high resolution scanner, and lastly a soft copy photogrammetric workstation for processing the imagery to derive image and vector products using digital photogrammetric workstation, which combines computer softwares, that is a graphic workstation, with in most but not all cases a stereo viewing device, a 3D mouse, and software configuration includes ADAS Imagine with Leica photogrammetric suite. For modern DPWs, there is no specific requirement for the host computer. Often a DPW can be built on a high-end desktop PCs with at least 256 RAM, 1 or 2 19 or 21 inches monitor and high performance graphical card. Ortho image generation using analytical stereoplotter, that is LPS. Imagine photogrammetry, formerly LPS, is a software application for performing photogrammetric operations on imagery and extracting information from imagery. Imagine photogrammetry is significant because it is a leading commercial photogrammetry application that is used by numerous national agencies, mapping agencies, regional mapping authorities, various DOTs, as well as commercial mapping firms. Aside from commercial and government application, Imagine photogrammetry is widely being used in academic research. Research area includes landslide monitoring, cultural heritage studies and more. Figure number 9 shows the flowchart for ortho image generation. To generate an ortho image, we follow the following steps. First, we will need a GPS control point with aerial photographs, that is stereo pairs with RPCs. RPCs provide a compact representation of ground to image geometry. Next, we will perform interior and exterior orientation. Interior orientation is concerned with the determination of set of parameters for the transformation from pixel to image coordinates. And exterior orientation represents a transformation from the ground coordinate system to image coordinate system. The exterior orientation is the position and orientation of camera when the image was taken. Next we need point generation. Features that type point generation, that is features you can clearly identify on 2 or more images. Next we will perform triangulation. Triangulation is measurement of series or network of triangles in order to determine the distance and relative position of point spread over an area. Then after this, precise observation at minimum error will perform. Then we will generate a DEM, and after this we finally generate an ortho image. Using a computer called Stereoplotter, the stereo pair can be viewed as a single image with the appearance of depth and relief. Ground control points are established based on ground surveys or aerial triangulation and are viewed in the Stereoplotter in conjunction with the stereo pair. In this setting, the image coordinate of an XYZ point in the stereo pair can be determined and randomly selected and digitized. These points in conjunction with the control points comprise the data points for the DTM. The accuracy of the final digital orthophoto will depend in large part of point density of the DTM. Now coming to the end products, we will get topographic maps, orthophotos, digital elevation model, 3D CD model, hydrological model and fly-through model. Coming to the advantages of photogrammetry, it covers a large area quickly. Second, it is low cost, though flights are costly, but it provides more applications. Next is easy to obtain access information of inaccessible areas from air. It illustrates great details, and last is 3D visualization. Now coming to the applications of photogrammetry. Photo mapping services provide solution to the highly specialized needs of today's world to compile datasets from photogrammetry such as the following. First is land surveying. Land surveying is the technique, profession and science of determining the terrestrial or three-dimensional position of point and the distance and the angle between them. It involves land use land cover mapping, urban planning, wasteland mapping. Figure number 11 shows area demarcation for land surveying. Next application is topographic mapping. One of the most widespread use of photogrammetry is topographical mapping, which is considered the primarily approach to GIS based data collection and updating. It provides topographical information of the area, and figure 12 shows the contour with the topography of the area. Next application is terrain models. It includes digital elevation model, digital terrain model, spot heights, contours and break lines, which in turn useful to superimposed over an orthophoto, useful to determine irrigation requirements, useful to determine drainage requirements, and ideal for rural property mapping. Next application is engineering designing. Using photogrammetry, 3D models of a busy intersection and railway junction can be generated. It also useful for urban infrastructure planning and also useful for infrastructure design, modeling. Now coming to the next application, that is natural resource and environmental inventory. Photogrammetric products are being used to monitor natural and cultural ecosystems, since it provides a wide area coverage with the various information like different objects showing different properties, which in turn can be used for interpretation. Next application is hydrographic survey. Photogrammetry provides hydrographical information of the area, which can be used in detailed drainage studies, 3D model of extensive drainage network, useful to optimize drainage systems, ideal for high density urban mapping. Figure number 16 explains the three-dimensional view of the flooded area showing streams, center lines and elevations. Next application is geological mapping. This technique allows to obtain a highly accurate 3D picture of the visible outcrop. The spatial pattern of joints in nature, it can be investigated using the software. This might help to understand how physical rock properties influence the spatial complexity of the fracture systems and develop constitutive scaling relationships for certain rocks. Figure number 17 shows the lithological map with the topography of the area. Now coming to the next application, that is medical photogrammetry. Photogrammetric measurements for the diagnosis and treatment of human conditions and for biomedical research in form of close range photogrammetry with its own distinctive challenges and constraints. Reports of fully digital systems are somewhat limited so far. Conventional photogrammetric techniques have been used for a broad variety of medical applications. Amongst them, craniofacial mapping, human trunk and extremity mapping, wound and sore mapping, as well as dental mapping are the most common. Nowadays, laser scanning and 3D probing devices have superseded photogrammetry for many of these applications. While photogrammetry has advanced to online measuring and real-time navigation application in the medical field. Figure 18 combines bone structure and 3D representation of skin. Next application is police investigation. There is an easier way to get all the information at an accident scene than walking around taking pen-stalking measurements by using photogrammetry to map the scene. Instead, your camera can help you gather all the important information quickly and accurately so that you can clear out faster and get traffic back to the normal. Next application is architectural photogrammetry. Photogrammetric techniques are being used for the representation of the facades or elevations of the historic buildings and structures. The most common product is the line drawing, which delineates architectural forms. Such surveys are needed by the various disciplines involved in building repairs and conservation. Next application is archaeological mapping. Using terrestrial photogrammetry, archaeologists can produce photographic planes of sites and their stratigraphy and can take accurate measurements directly from the photos and import photographic data into other computerized techniques for mapping and visualizing the archaeological features. The production of a photogrammetric image involves the combination of number of technologies: total station surveying, traditional archaeological photography, geospatial reflection. By combining these technologies, we are able to produce a hybridized documentation technique that can serve many purposes. Figure 21 shows the 3D model of an archaeological site. Next application is industrial machinery. Photogrammetry has been increasingly applied as a precise 3D measuring tool in industrial and engineering works. Analytical photogrammetry is now routinely employed in tasks of measurements like machine tool inspection, fixture checking, structural deformation monitoring, provision of control disabilities to guide, structural deformation monitoring, provision of control database to guide, industrial robot measurement of structural or in the earth orbit. Photogrammetric method has advantages of non-contacting 3D object reconstruction by means of spatial rays. It provides a short recording time on site, nearly independent from the amount of object point to be measured, and the possibility to choose the recording station in a very flexible way. If a dynamic or kinematic process has to be recorded, photogrammetry seems to be the only way to measure a whole object simultaneously. Next and the last application is military application. It involves the use of mosaics. Mosaics is an aerial photograph of a large area made by carefully fitting together aerial photographs of a smaller area so that the edges match in location, and the whole provides a continuous image of the larger area. Mosaics are intensely being used by military projects because they provide synoptic view all over the target area. target planning, topography of the area, decision making, etc. Figure 23 is mosaic of military planning. So, this is all about digital photogrammetry. Hope you all enjoyed it. Thank you.